This talk will be on implementing X.509 path validation for Python. My name is Woodruff, and I work at Trail of Bits. So for those of you who don't know, Trail of Bits is a research and development company. We're based in New York City, but in reality, we're like 70% remote, and we're based all around the world, really. I run we call it the ecosystem security team, but it's really the open source team of the company. We do a lot of work on various open source ecosystems, basically sticking our noses where we don't belong, adding security features, improving things, maintaining things that people don't want to maintain, and getting paid to do it. So happy to talk more about that. Happy to introduce you to my colleagues who know about their respective parts of the company as well afterwards. But yeah, just to set the stage for what I want to talk about, I'll do a quick recap. I know pretty much everybody in this room at least is roughly familiar with X.509, but I'll do a quick mode set on it. Talk about what path validation for Python looks like, pre-existing efforts, implementations. I'll talk about the work that went into designing implementation from scratch. Finally, going into our actual implementation. Next, we'll talk about testing the bejesus out of it. Basically, we were so afraid. Yep. Yes. How do I do that? Better? Yep. Nobody should really want to do this. You should be really afraid when you implement path validation. And so we were afraid. And so we did a lot of testing, and we'll talk about the efforts that went into that, as well as into X.509 Limbo, which is our reusable test suite for path validation. Talk about testing other implementations, and then the bugs we found everywhere using our test suite, which you will hopefully all be able to reuse after this talk. And then finally, we'll talk about lessons learned and future work. Yeah, so before I get into any of that, I wanted to offer some thank yous. This work, like I said, we're a consultancy, and our work is funded in part by nonprofits. And so in this case, it was funded by the Sovereign Tech Fund in Germany. We worked very closely with the PyCon maintainers, one of whom is Paul, who's here, who defined the bounds of this work and dealt with our constant badgering over 9 months as we'd actually developed the work here. X.509 Limbo was their idea. We just built it for them. I also want to thank Filippo. He graciously allowed us to merge this work into C2SP, and then also roughly inspired the design for the actual test suite that we built. And then finally, I want to thank my colleagues, Andrew, Facundo, and Alex, who all designed, discussed, and engineered components of this work. And then just on the bottom here, you can see, this has been sort of in flight for roughly 9 years in terms of people wanting this thing in Python. And so only this year did it actually get done. Yeah, so like I said, the big banner item here is Python cryptography now has X.509 path validation APIs. The thing that you've always been doing, which is pip install cryptography, works right out of the box. I'll do a screenshot of the API in a second, but it's written in Rust like a lot of the other X.509 stuff in Python cryptography. It's only about 2,500 lines of new code, and there's no OpenSSL with a little asterisk that I'll get to. Yeah. And then, like I said, X.509 validation is fundamentally scary, so we tested the crap out of it. This QR code leads you to a URL, which is the website for X.509 Limbo. It has all the test cases that you can browse through and see how we've categorized them. And then we want you, as people in this room who I know work on a lot of this code, to integrate this into your implementations or bring it to people who you know who do, and make your implementations better. And just to give you a preview, it's already found bugs and discrepancies, including one CV in other implementations. So yeah, and this is like a really high level of what it looks like. I mean, I'm not going to stick too long on this, but you get the idea. You load trust root, intermediates, leaf, and you verify with a policy. So it's a quick mode set on X.509. I'm going to start with like a bucolic picture because we all agree that X.509 is secretly, well, I'll start with a bucolic picture. X.509 is a public key conveyance format. Essentially, it's a binding between a public key and some subject or other metadata about that key. That metadata includes expiration, policies, etc. That is then signed over by a private key that you keep secret, obviously, and usually, when it's not a self-signed certificate, it's a private key from another certificate, which itself is in turn bound to other metadata. This makes X.509 fundamentally a chaining primitive. It's a way for certificate A to sign for certificate B, which in turn conveys down this chain finally a public key that you want to use in some other application. It's not a one-way key-to-cert mapping. Famously, you can have cross-issuance and multiple issuances under the same keys, different names. And all of this causes sort of complexity at the chain building layer because you now have self-signed certs and you have cross-issued certs and you have certs that have cycles because people misissue or just fuck up, essentially. X.509 is also a protocol for securely introducing principals to each other. The chaining primitive allows us to go from a trusted a priori root, some certificate, to a site or some other principal that we want to connect to via a sequence of untrusted unknown principals or entities, essentially. That's the thing we call chaining, and you can also do it vice versa for what we call like mutual or client authentication. Like I said, it goes through these, in theory, untrusted intermediates who hopefully don't have cycles like that. And then finally, last but not least, X.509 is a complete dumpster fire of an ecosystem. As you all know, 75% of the world runs on OpenSSL and its forks. Those forks are often better, but severely constrained by API and ABI compatibility with the OpenSSL ecosystem. OpenSSL's X.509 implementation is like half RFCs and half like, and the other 25% of the world's X.509 is NSS, OSS, open source operating system implementations, embed TLS, all these other smaller open source ones, and then a bunch of like vendor crap that exists at various layers of like the OS and like appliance stack. And some of this stuff is run on like hardware appliances that nobody remembers. They're just running in a closet somewhere. This all combines with DIR's sort of like bug magnetism to produce this incredible like playground for policy bugs, logic bugs, memory corruption bugs, things that range from like pretty trivial, not super severe, well, kind of severe like DOS, to very, very bad things like heartbleed, which I know is at the TLS level, but gives you the impression of the kind of things that you can disclose remotely by this sort of like massive complexity of crappy parser code. And then those CVs don't really matter. Yeah, so now that we know what X.509 is, let's talk about it in Python. So to give you a bit of status quo before we get into the work itself, Python does have X.509 APIs. It has this standard library called SSL, which is a relatively thin wrapper over an OpenSSL, which made a lot of sense back in probably 1996 when this was first written, because OpenSSL was really the only game in town. There are internally maintained copies of CPython that the CPython developers know about that instead use Bourne and LibreSSL, but these are not officially supported by the CPython upstream. And for better or worse, the SSL module is very tightly tied to Python's socket standard library APIs, which means that it's very hard to reuse outside of secure socket contexts. And then finally, because nobody wants to deal with OpenSSL, basically nobody maintains it, which should not be a particular surprise. And so to get around this limitation, which is you can't use it outside of sockets, there are a large variety of third-party libraries that are typically wrappers over OpenSSL or wrappers over platform validators that exist to sort of cover this gap. And unfortunately, pretty much all of them are pretty easy to misuse, either because they're thin bindings over OpenSSL and therefore expose like reference counting semantics that really shouldn't be exposed to a memory safe language like CPython, or they just expose like the lowest level of OpenSSL APIs, or OpenSSL is just plain hard to use, and so the APIs reflect that difficulty, and people in turn reflect that in the buggy code they write. There is one exception to this, which is cert validator, which is a pure Python X.509 path validation library that we took a look at as part of this work. It pulls from the OS APIs by FBI, and it does have a generic API, but as we'll see, it has some pretty significant bugs that don't stack up super well. Yeah, so I want to talk now about some of the design constraints that went into the actual work we did as part of this. And so just to start off, after consultation with the PyCon maintainers, we came to sort of a general agreement about a baseline set of features. We want TLS certificate validation consistent with the CAB forum guidelines, which means, of course, DNS and IP names for subjects, name constraints, and RFC 5280 and 6125, which is the wildcard RFC, and then some additional crap on top. We explicitly excluded all this really well-known, like hairy stuff. Some of these things are good. I mean, certificate transparency is great, but we didn't include it as part of the minimum viable product here. And then finally, most importantly, all of this actually needs to fully exist within Python cryptography itself, which means that pip install cryptography needs to continue to work on every platform that it currently works on. It needs to be only Python and mostly dependency-free Rust, and needs to meet the extremely obsessive requirements of the PyCon maintainers, which include 100% test coverage, correctness over known problematic inputs, and the fact that they're speed freaks. It was a great idea. Yeah, then I want to talk a bit about design principles. I don't think anybody actually calls these Sleevy's laws, but I read Ryan Sleevy's post so many times while doing this implementation that I think of them as laws at this point. These are sort of general guiding principles we followed as we built the path validation algorithm. One to really think of is, and I think it's the most important one, is that there is no one true chain. Many implementations like OpenSSL think in terms of like a top-down construction approach where you find a chain, you do some additional validation after it, and if it's invalid, you just reject it, and then your connection just fails because, well, the chain you built is invalid. The reality is that path validation is like this dynamic graph traversal problem where you have to revert back to a previous state in your chain building chain construction and try additional new paths if you have invalidated your chain in some way, such as via a name constraint. So in reality, it's like this abstract dynamic depth first search problem with changing constraints. as part of this, you have to encode rejections into the search itself. You can't reject things after it's built. And then finally, you have to sort of like know your limits as the actual implementation, things that are outside of the standards themselves. The standard doesn't have any say about arbitrarily deep chains, extremely large name or policy comparisons, or anything else that would not actually appear in a real PKI. Instead, your implementation should do the reasonable thing and not allow people to run, for example, 500 million name constraint comparisons and DOS your server. Yeah, so just to get into actual implementation details a little bit. So implementation is 90% Rust, 10% is Python. It's mostly API scaffolding for actually bringing the Rust APIs into the Python layer via pyo3. The Rust composes the trust store, policy logic, the key, SAN, and name constraint parsing, and then the core path building algorithm itself. And then there's a bunch of pyo3 scaffolding in the middle. And then finally, the pure Python side is we have this policy builder API that you can actually use to construct one of these policy objects, and then a bunch of small types and type hints and aliases and things to sort of make the developer experience pleasant. And then finally, of course, we didn't actually do the work on Cryptography's X.509 parser. That was pre-existing, incredibly difficult work that the maintainers did. And so we sort of slotted our work into that. But you might ask, like, with all this, like, where's the actual cryptography, right? Like, all I've talked about so far is sort of like logic and parser crap. Well, if you dig into the cryptography, the X.509 validation code a bit, you'll notice that we have this like crypto ops trait, which has this really convenient verify sign by function, which takes assert, which you're verifying, and the key that you're verifying with. And these are, of course, associated types, so they don't really tell you anything in this context. However, if we dig a little bit further, we'll notice that crypto ops is implemented for pycryptoops, which, of course, implements key as a abstract any object in Python. And then we have this verify sign by function, which captures the Python GIL and runs this huge function called verify signature with signature algorithm, which takes the key, turns it into something as ref, takes the signature algorithm, and a whole bunch of other ASM1 stuff. So this doesn't really answer the question at all. All we know now is that our pure Rust code is suddenly calling into Python. And so the mystery continues to thicken because we go to verify signature with signature algorithm, and all of a sudden we're calling things via call method 1 with pyverify, which, in case you aren't aware, means that at runtime we're now looking up an attribute on a Python object called verify, which is a function, and we're calling that attribute as if it's a method with this input signature and data. So again, this really doesn't answer our question because now we've just gone like another layer of indirection into the code base. And it gets even more confusing because this verify method that we see that's called via a string, like a string lookup, is actually an abstract method in an abstract base class. And so you start to think like, well, what the hell? Like I'm not actually getting anywhere with my like discovery of where the actual cryptography in this is. But then you start to notice, well, it's an ABC, so it has to be implemented somewhere. And so you start to look for registers on that ABC, and you notice something scary. You notice rust _ OpenSSL.ec.ec public key. And you keep digging, and you find a Rust file which binds OpenSSL into Rust via Rust OpenSSL and calls essentially Rust's bare signature verification, OpenSSL's bare signature verification APIs, which of course means we are back to C. So after a great deal of work and after a great deal of sleuthing, we find that we haven't fully gotten rid of all the C in X.509 validation in Python. Unfortunately, under everything, there's still a little sprinkling of good old-fashioned OpenSSL calls. So, like I said, that asterisk comes back, and it turns out that OpenSSL still provides the core cryptography of our algorithm. Carefully nested behind the abstractions, hidden away so that in the future, that ABC can be swapped out, and any other verification implementation can be swapped in, and it can become pure Rust or pure anything else, but still there because, well, implementing cryptographic primitives is pretty scary, and nobody really wants to do it. But nothing else. X.509 parsing is pure Rust. The chain building and policy conformance is also pure Rust. And even the SPKI parsing and key extraction, which is like the really nasty stuff, is also pure Rust. And I like this quote from Alex, where basically I finished the initial implementation here, and then he set off to make it way faster, and he replaced the SPKI parsing from OpenSSL with a pure Rust one, and it didn't make SPKI parsing 60% faster. It made the entire certificate path building process 60% faster, just by replacing OpenSSL's SPKI parser with one written in Rust, which is crazy. Yeah, so let's get into testing since I've talked a lot about implementation. So there's the obvious thing we do, which is we write unit tests. We can do a lot with unit tests in both Rust and Python, but not enough. Remember, Python cryptography requires 100% test coverage, and the backend abstraction that we've chosen, where there's like this ops that gets produced from Python, means that everything after signature verification needs to happen in Python because Rust can't obviously produce like a CPython interpreter out of thin air. And then we tried to do this, and we tried to instantiate the CPython interpreter inside of car test, and like, crazy shit happened, which you can see in that screenshot. So we need a way to reach like edge cases and annoying pathological cases that are beyond signature checks within the validator. Things that are gated on extension checks, criticality, the current name constraint set, et cetera. In effect, we need a framework for rapidly churning out graphs and chains that contain all sorts of like, strange pathological inputs that can come into from like a real client connecting to a server. So that brings us to X.509 Limbo, which is our test framework for doing this. The good news here is that we set out to do this, and we looked around, and it turns out there's a lot of pre-existing work, very, very hard work that's been done to write path validation and PKI testing frameworks for various implementations. Netflix has this really fantastic one, Better TLS, which we ended up integrating into our test suite. There's X.509 test from Google. There's these PIT v2, 1, 2, and 3. And each of these, unfortunately, has its own bespoke test case in vector format, but in some cases, we were able to unify them and haul them into our little JSON blobs. And yeah, like I hinted, I mean, X.509 Limbo is fundamentally a giant blob of JSON. Each test case is the set of root, intermediate, and leaf certs, as well as the expected results and any additional constraints like domains and expected key usages and extended key usages, et cetera, that we expect the validator to check. Contains both our own sort of like handcrafted tests as well as Better TLS at the moment, and we're looking to integrate others. And then finally, this may come back to bite us, but we've grouped it into namespaces for the time being. So for example, we have WebPKI NC for name constraint tests under the WebPKI CabF profile. Yeah, and this is what writing those tests look like. I mean, they're currently Python, so you can tell, we have this little builder API. You can tell it's generate a private key, generate a root cert with that key, generate a leaf cert, and then the builder says, oh, I'm going to build a test case that does server validation. Here's the trusted root. Here's the pure cert. There's no intermediates in this case. Here's the expected pure name, and then we expect this test case to fail because under CabF, the root cert should not convey a P192 key. So that looks like that. And then as JSON, well, it's just JSON. Yeah, so we did all this. We made it reusable because we want other implementations to integrate X.509 Limbo into their test suites. I didn't do this with the expectation to maintain these harnesses indefinitely, but we created a whole bunch of basic harnesses that run inside of X.509 Limbo's repository to test to make sure that our test cases basically make sense and are consistent with other implementations. And in the process of doing this, we found and/or surfaced a bunch of bugs in these implementations. We found a whole bunch of false verifications and incorrect failures, meaning chains that should have been rejected, or rather accepted that should have been. I'm confusing myself. Anyways, there are a lot of name constraint bugs, as well as one memory corruption bug in GNU TLS. This one was actually an out of bounds mem copy, which was bonkers because this is like a pure logic operation we're doing. There should not have been any memory corruption whatsoever in any of these implementations. But it turns out, to make things even better, that this bug was surfaced by a Better TLS test case, which had previously been integrated against GNU TLS, but they had just skipped this test case. So this test case was in the public for years, for about 6 years, and we just happened to run it and find the crash. So if you want to look up the CVE, I'll show you the slides as well later, but it's 2024, 28, 835. Yeah, so some lessons in future work. One of the lessons we learned is that the standards and the actual implementations don't really agree in the real world. 5280 and CabF are pretty prescriptive, and then in the real world, our implementations are just all over the place. CabF says to always prefer the SAN. Many implementations check the subject or both, and then have sort of complex behavior around when the two don't match. Many implementations don't even bother with serial number checks, but despite the fact this is like the main bug that caused the exploitability of Flame back in 2008. Most implementations have at least one name constraint bug causing a ton of false negatives, chains that should have built that weren't built. And these typically appear in cross-issuance and self-issuance graphs, which are the most critical ones because those are the ones that you ultimately end up chaining to in sort of these like complex, outdated old OS install scenarios. Sort of along with that, many implementations don't handle self-issued cert path length correctly, and many don't enforce the presence of SKI and AKI, which is not a huge deal because this is purely an optimization, but profile says you should do it, and so you should do it in terms of consistency. Even outside of the standards, our X.509 has plenty of quirks that are good to lawyer over. There's a classic one of X.509 5280 says that certs must be 20 bytes, but when you encode a negative number in dir as 20 bytes, it might be 21 bytes because of the sign bit. And so is that valid or not? It's not clear. Most implementations that do check this ultimately allow 21 byte serials to allow for it. RFC 5280 says that 0.9 repeating does not equal 1. This is a classic source of like much grievance in the web PKI. Then, implementations talk frequently in terms of root certs. The RFCs don't really have this concept of root certs. They talk about trust anchors instead. All these things like expiries on roots, name constraints on roots only matter if you think in terms of root certs. Unless you're CABF, in which case trust anchors don't exist and only roots exist. So the two don't really agree on language there. And then similar to that, it's not clear whether conveying a trust anchor as a certificate means that you have to respect its extensions and constraints. There's sort of dual perspectives there. We chose as part of Python cryptography to respect constraints on roots, but other implementations like REST-TLS choose not to. But also some browsers do some of the time, and it's not really clear when they do. So that's something that I wish there was some more clarity on. And then finally, it's not clear whether the Leafs pub key is subject to CABF constraints because the Leafs pub key is conveyed. It's not necessarily a thing that's being used for signatures. So it's just sort of not super well standardized or specified. Finally, despite all this complexity and ambiguity, things are pretty good. Web PKI is still kind of a sort of dumpster fire, but it's in a lot better shape in 2024 than it was in 2014, thanks to the hard work of the CABF folks. Overall, shorter validity times meaning they can rotate into stronger policies and stronger requirements faster and faster. Things like CT, and then just generally higher expectations when it comes to what CAs are doing behind the scenes. No more shenanigans around BER or malformed roots, no more V1 roots, no more secret intermediate CAs that get issued to man in the middle of the entire internet, things like that. The hardest part ultimately that came out of all of this was not so much the actual implementation, but determining which parts of PyCA were allowed to diverge from other major implementations. So obviously we wanted to do part of the point of replacing OpenSSL is to do a better job in these things. And so it's not good enough to implement this and then sort of regress back and do all the same bad things that OpenSSL by default does. And so a hard part was determining like the break budget for the Python cryptography implementation. And despite all this, after we rolled it out, we still found a few bugs, which we then promptly turned into X.509 limbo test cases. For example, we forgot a root key strength check. There was a unknown name constraint handling bug where name constraints that were just of like an unknown OID and we didn't already support would be silently passed, even if there was a similar typed SAN in the chain somewhere. And then finally, we just ignored time zones on date times for a while, which was my bad. Yeah, so with that in mind, some future work we want to do. At the time that I wrote this, the only thing we had implemented was TLS server cert validation. Last week, the PyCA cryptography folks maintainers merged client cert validation. So this is now in. It's not in a release yet, but you can check it out on the docs on cryptography.io. Going forwards, a lot of users have so far expressed interest in other profiles besides 5280 and WebPKI, things like SGX and Authenticode. Users beyond these other sort of like more esoteric profiles want even more control over the profiles or the individual knobs of the profiles. And these are usually bad things. So it's not clear whether we should actually expose these things. But it's good to know they want them and something to think about. And then generally, as a guiding principle going forwards, the knobs and config points that are exposed via the default paths here should not make the current APIs harder to use. They should continue to be relatively misuse resistant. Should continue to guide users towards what is the 99.999% case, which is the WebPKI path validation. And then finally, we want to continue to sort of talk about and evangelize X.509 Limbo. We want more implementations to use it directly upstream instead of hosting our own harnesses. We want to cannibalize more related test suites and support additional profiles besides 5280 and CABF in the test case suite. With that, thank you. I think I have like a few minutes for questions. Yep. Good.
Should X.509 Limbo?
Believe it or not, it is in there. Yeah. Yeah, Filippo did that like 2 weeks after we went public with it. So thanks. Yep. Yeah, so it's not part of the current external test suite for Open. It's not currently integrated into OpenSSL's test suite. We have, and I can show this. We have this website which has anomalous results for each implementation. And so, for example, I can click on these are harnesses that we wrote as a team, and so you can see like OpenSSL unexpectedly verified a 0 serial number cert. And this is pretty pedantic because in practice this probably doesn't matter a lot, but we're running these locally instead.
That's like real numbers, like
Yeah, there's a philosophical argument that like a lot of these requirements are obligations of the CA to enforce, and if you do them locally, well, you're on your own. So
Also, testvector also spur.
that's very good to know. I've never said it out loud. Yep.
App building.
I would say no, but Alex is a speed freak, and I'm saying that publicly. So I think faster is better, and it didn't really hurt the readability of the implementation.
There are some applications. And this other. Probably not in TLS. On TLS claims.
Yep. All right. Any other questions? Yep.
Just like that, Rust is obviously good. However, Python's also like perfectly expressive and all this.
Yeah. So I would say the number one justification for doing this in Rust is that the X.509 APIs in Python cryptography are much more detailed on the Rust side than they are on the Python side. To do the path validation that we want, including policy checks within pure Python, we would have to port out a bunch of internal APIs that are only on the Rust side, which in turn would mean it's downloaded 10 million times a day. Users use all kinds of private APIs when they're told not to. Exposing all those things is just a recipe for disaster when it comes to user misuse. Exactly. Yeah. Yep. Great. All right. Thank you, everybody.
Thank you very much.